Awesome. So my name is Bryson Ewanchuk. I'm the technical advisor for ranging within Halliburton. Just a little bit about myself. I've been involved in over 100 wellbore intercepts, some of that being foot on the ground, others just in planning processes. I've also had the privilege of being involved in the deepest relief well in history. So for the presentation today, I'm trying to bring some of the lessons that we've learned in oil and gas, primarily in wellbore intercepts, and kind of bring it into the geothermal space here. So. Starting off here, I have a slide just on the evolution of geothermal wells. I know we've seen this a bunch of times, so I'm just going to go through this very, very quickly. So kind of going left to right here, we have the direct use geothermal. Nothing too complicated from a drilling perspective, just drill down a couple hundred meters or so, find a geothermal reservoir, direct access to residentials. Next, we have the hydrothermal resource reservoir. This is kind of where we're at today. This is what's more or less conventional. So fundamentally, we're trying to be finding these fractured reservoirs. It's a little bit tricky to find these, as we've kind of learned throughout this conference. So it's a little bit of a costly endeavor to drill these wells, to have them flow through this already kind of pre-fractured location. Next, we're then talking in kind of in the more advanced guys here. So I'll just click these ahead. So we have the EGS and the AGS systems. So the EGS, we're inducing the fractures ourselves, but the same kind of concept, pumping fluid down one well, having flow through those fractures into the other well, and obviously getting the returns that way. And then finally, this is kind of where I get involved here, is the AGS systems, or the advanced geothermal systems. So there's kind of two styles. There's the tube-in design, or the concentric cylinder. So you pump fluid down one side, it heats up, it comes back the other side. The one that I'm really particularly interested in, though, is the underground loop. So ultimately, we try to connect two wellbores. We try to make an underground radiator, pump fluid from one side, it heats up, comes out the other side. So let's talk a little bit more about kind of the AGS system and some of the challenges that it has here. So this little illustration on the left here, I guess that's it, right? You have two wells, just connect them, right? How hard could it be? So we drill one well down, we drill a second well, we hopefully try to intercept it. The trouble with this, though, is we're intercepting these well bores at the deepest part. And at the deepest part, it's also the hottest part. This is an extreme challenge for us that we're always trying to mitigate. So this image just to the right of the illustration there, this is a real world example that we've done. So this guy here, it's about 5,500 meters deep, and it was quite hot, as you guys can see. So this is kind of a real world example of us drilling one of these YouTube style wells. So just another kind of point to this, wells can be drilled vertically or horizontally. It doesn't necessarily change the complexity all that much. So why is it challenging to drill an AGS? Well, it all comes down to air. So everyone likes to think they know the wellbore position of where their well is, but the fact is there's the little inclination kick here, the little bit of drift here. It builds uncertainty. This uncertainty, it happens in three dimensions, obviously in the depth, in the azimuth, and the inclination, and it also compounds with depth. So think of it as an ellipsoid, and it just gets bigger and bigger and bigger. And this is not only just on the target well, the one that we're trying to hit, it's also on the drilling well. So on the left here, I have a really good image. This is an AGS style well that we were drilling. It shows the ellipse of uncertainty at the interception point. And just to put this into perspective, we're trying to hit something that has the diameter of about a dinner plate, right? The ellipses of uncertainty, if it's a good well that has really good surveys, the ellipse of uncertainty might be double the size of this room. I've been in ones that are the size of soccer stadiums. So we're trying to hit something. We're basically trying to, thread a piece of spaghetti through a wedding ring, if you will, from the top of the building. So this is the largest challenge in every wellbore intercept: is how do we manage the air, right? Every well has it. We have to get rid of it. So what do? Well, we use what's called magnetic ranging. So this image has a lot going on. So I'm just going to kind of walk everyone through it. So on the left-hand side here, I have two wells. I have a drilling well and then a target well. The target well is going to be on the right-hand side there with that kind of red ice cream cone on it. So what that is representing is, as we're drilling deeper, the ellipse of uncertainty of where that wellbore could be is increasing. So from the side view, it kind of looks like a cone. So we can call it a cone of uncertainty. On the drilling well there, oh, is it? Okay, gotcha. There we go. So this blue kind of pizza slice here, you guys can all see that? So this is what we call a magnetic ranging shot. So I'm going to explain what that is. So just on the side here, A magnetic ranging shot is determining a distance and a direction between the two well bores. So with this distance, there's going to be a little bit of air. There's going to be a little bit of air on the far side and a little bit of air on the close side. As well as when we're referring to direction, the well could be a little bit more to the left. It also could be a little bit more to the right. So when you put all those airs in together, it makes this funky shape called an arced sector, or like a chunk of a donut. It's kind of how I like to think about it. So when we're using magnetic ranging, the goal is to get this ellipse of uncertainty, how big it is, and we're going to shrink it down to that chunk of a donut. Magnetic ranging also works opposite of traditional surveys. So as surveys get bigger with depth, magnetic ranging, we actually get smaller and tighter as we get closer to it. So that's how we're able to perform wellbore interceptions. So what is magnetic ranging? Well, the textbook definition of it, if you will, it's the use of a magnetic field, either natural or induced, to determine a distance and a direction between two or more wellbores. To put it simply, think of it as an underground metal detector. That's the best way to kind of think about it. So this magnetic field can either be from existing tubulars or it could be from a source that we deployed in the ground. So the fundamental 3 steps of it is we generate a magnetic field, we try to detect that magnetic field, and then we try to determine a distance and a target to that magnetic field. So how do we generate a magnetic field? Well, there's 4 ways. To put it simply, if you just have a piece of wire, if you have a piece of wire, you run a bit of current through it, this creates an axial magnetic field that we're able to pick up. If we take that same wire and wrap it around itself, we now just made an electromagnet, or a coil, or also a solenoid. Over here on the exit door, that metal lock, that's actually a solenoid right there. So they're kind of everywhere. Next, we have permanent magnets. So think of your magnets that are on your kitchen, on your fridge. These ones are a little bit more high tech, but it's basically the same thing. Think of a north-south bar magnet. So that's what we got there. And then finally, we have just the remnant magnetism that's left on tubulars. So this could be any metal. Basically, any metal that has any form of iron in it, we can detect to some degree. So that's what this is talking about. So how do we measure magnetic fields? Well, to put it very simply, we use what's called magnetometers. Everyone here has used a magnetometer. They're in your cell phones. It's how you have the compass, right? So it's a 3-axis sensor that's able to figure out a direction and an intensity at a single point in space. We take this one step further, though, and we use what's called gradiometers. So what gradiometers are is if I took a series of magnetometers and wired them all together in a grid. Okay, just imagine that for a second. I'm gonna change this to sound for a second. So pretend I didn't have this microphone. If I started talking, the individuals at the front here would hear me pretty good. Individuals in the back, it would obviously be a little bit more quiet, right? There's a decay. So if we know the positions of each of the individuals, like the distance between, and use a little bit of math, we can actually back calculate out, based on those known positions, where I'm standing. This is the same way with magnetic fields. So magnetic fields have a predictable decay. We know the initial intensity of where this should be. We have multiple sensors that are monitoring the decay between multiple points. And from that, using a little bit of math, we can actually back calculate out and get a direct measurement to a target. I know it's a lot to take in, but it works. So with this all being said, us and our gradiometers and how we make magnetic fields, we have a whole list of ranging applications and categories. To put it simply, and to break it down very simply, we use magnetic ranging when we want to hit wells, and we use magnetic ranging when we want to dodge wells. That's it, put very, very simply. So there's obviously a list of applications that I could spend, an hour or 2 talking about, but maybe for another day. But the other thing I want to get to is we have what's called access-dependent and access-independent solutions. So what that means is access-dependent means we need access in that target well. We need to put a sensor. We need to put a magnet. We need something. We need a target, right? So we need access to that target well. Access-independent systems mean we don't need access to that target well. We're able to range without needing to access that well. So when I'm talking about this, think relief wells, right? The well's on fire. We can't get there, right? So that's kind of what I'm getting at. So every ranging job generally falls within this matrix. It sometimes takes bits and pieces from all of this, but this is, kind of a really good summary, I'm going to say, of it. So next, we have our ranging technology fleet. So starting off on the left-hand side here, we have our MGT system. So the MGT system, it stands for the Magnetic Guidance Tool. The Magnetic Guidance Tool is basically a large coil of wire. We take this coil of wire, we put it in the target well. From this, we send current downhole. It generates a massive magnetic field. This magnetic field is then picked up by the MWD sensors, and we're able to get a distance and a target between the two wellbores. Next, we have the RMRS system. The RRMS system stands for the Rotating Magnet Ranging System. The way that this system works is that directly behind the bit, we have a bit sub. The bit sub's about yay big, and it's jam-packed full of rare earth magnets. They're extraordinarily strong. So what happens is when the pumps are on and that bit is spinning, this giant magnet is also spinning. It's creating a very large, distinct field. From that, in the target well, we run a sensor, a wireline sensor. That sensor is able to pick up that spinning magnet, and it's able to figure out a distance and a direction between the two. Moving on to our access independent systems. So starting off, we have our well spot system. So well spot is it's our interception tool. This is the primary tool that we use for wellbore intercepts. It doesn't need access to the target well. The way it works is that there's a wireline sensor at the bottom here, and about a couple 100 feet or so above that, we have an excitation source. And what I mean by that is we send electricity through the formation. Some of this electricity works its way onto the target well. It then goes up and down that target well, making a very small magnetic field. And from this, we're able to pick it up with that sensor. So this is the primary tool that we use for all access independent wellbore solutions. Next, we have our PMR system. So PMR stands for the Passive Magnetic Ranging System. So this isn't necessarily really a tool, more of kind of a very advanced software that we use. So what it is that all tubulars that have iron in them are going to have a little bit of magnetism left in them. A lot of non-destructive testing that they do on the threads, that's also going to leave it's going to leave them magnetic. So what we're able to do is we're able to drill near the collars and pick up that magnetic signature and actually use that remnant field that's just left on it to figure out a distance and a direction between the two. So this system isn't necessarily a standalone system. It's more or less used complementary to combine it with others, but it could be used standalone depending on circumstances. And then finally, we have our Aurora system. So the Aurora has kind of overtaken our MGT system. So what it is rather than having a wireline unit that connects to a coil, we have a very large power supply on surface. We plug that power supply onto the wellhead and we shoot current downhole. This generates an axial magnetic field that we're able to pick up. So it's a limited wireline. So from our fleet here, we ultimately can use any combination or any individual one of these tools in order to drill at AGS. Every well is different, right? So we have to take in all the parameters, see what's best, temperature limits, things like that. So what I'm really excited to show is we came out with a new tool. So you guys are some of the first people outside Halliburton to see this. And the system is, it's so new, it doesn't even have a name. So we're referring to it as the Geothermal Ranging System. So it's a new concept and it's a new tool. So the basic concept is that we have two drilling rigs drilling at the same time. In one rig, we have a brand new tool, which is called the excitation collar. So the excitation collar gets connected to the iCruise rotary steerable system. Oh, I'm dead here. So in the top well there, long story short, the iCruise generates a lot of power. This collar also has internal turbines. So as we pump fluid down, it charges up. And it's a solenoid-based collar, which it actually generates a large magnetic field. So the system's designed quickly enough that we can be drilling a second well simultaneously. In that second well, we run our base star MWD, which has pretty souped up gradiometers, I'll call it. Ultimately, we can drill two wells at the same time, continuously ranging to each other. So this is the fastest option that we were able to come up with. So it's able to eliminate the need for wireline, which is massive, and it's the fastest possible tool for a wellbore intercept. Just a few more kind of notes on it. So you guys can see the solenoid-based collar on the top there, the base star system there below. The system's designed, as I said, to work with 2 rigs simultaneously. That being said, we could also substitute out the second well with a wireline. So it's not necessarily needed, but it's recommended for speed. Some facts on this, though, is the detection range. So this tool is able to see up to 400 feet away, 120 meters. So generally, ranging systems work really good far away or really good up close. This tool is able to range the entirety of an AGS well, from the beginning all the way out to get your, the thermal gradient between the 2 wellbores, and then back and provide an interception. I then want to highlight here the temperature rating, so 160 Celsius. So everyone's eyebrows are probably going up and saying, oh, that's low, that doesn't work. This being said, this is the lowest temperature limit, like this would be the lowest limiting factor of the system, but we don't run it by itself. This system is run with insulated draw pipe. It's run with mud coolers, systems like that, which actually can keep it alive. So though it seems low, it's a number we're trying to improve. It's actually not a problem because we just need a system around it that's in place for it. So yeah, so just an update. So this tool is, as I said, extremely new. This is kind of where it's at in terms of its development. So this is a picture of it right here. We built a whole bunch of them. We've calibrated a whole bunch of them. You guys can see here, it says first field trial planned for April. So while I was flying here, it actually completed its first official trial at our test well. It was going to intercept like the well, but the rig broke and they had other timing constraints. So rather than allowing to finish the intercept, they just said, you know what, this is good enough. So it's scheduled for its first customer use in 3 months. And yeah, so it's the first tool designed specifically for AGS. That's all I got for you guys.